Okay, let's get started. This is cs260, and we're on week 3. And this week's topic is about a new data structure called the linked list. And also, we will discuss some algorithms regarding search. As you know, like in a list, right? When you search some element in the list, you can choose to search the whole list and get and find out if the element is in the list or not, or if we know there's certain property in the list, such as this, if the list is sorted, then you can use some additional information to help find the target faster. So that's the topic of today: is how to efficiently search an element in a list that is sorted. So let's start with looking at one problem. Okay, so here is the problem. So you have an array of integers which is sorted in ascending order. Okay, and given a target with the list, and you will give me the index to which the target exists. If the target exists in the list, give me the index of that number in the list. If it's not existing, then give me a -1. So the requirement is that you need to get this as efficient as possible, right? In other words, how you search it more efficiently. So the normal approach is basically iterate through all the element in the list, right? So for example, here is I have a list of -1, 0, 3, 5, 7, 9, and notice that they are sorted in ascending order. Then what you can do is to go through this list entirely and look for, do we have a target? For example, if target is 9, and so I'm going to go through all the list, and finally at the end we went through it. We find the target. Or if the target is not in the list, we also know when we are reaching at the end of the list. So by average, if you do the linearly, the order of the runtime complexity is O of n, which means you need to search the entire list to get your answer. However, because this list is sorted, right? You can think about, maybe we can do it faster. All right. So, for example, if our target is 3, for example, right, and you can, first of all, let's say pick the middle of element, right? Okay, so let's say the target is 9, right? You pick the middle, maybe let's say 3, right? And because you know that the number is sorted, so our target is 9, 9 is greater than 3. So naturally, you know that the number cannot exist in any indices that's lower than 3, right? If you start from 1, 2, 3. So lower than 3, you don't need to search it. You can only need to focus on searching the upper bound or the upper section of this list from 3 to 9. And then you pick within those four elements, you can pick the middle point. Again, let's say 5. And 9 is greater than 5. So you can you divide this problem in half again. And how many times you need to basically finish the searching, right? So for example, if you have a list of 1024 elements, you divide it by 2, right? You get 512. And you divide by 2 again, you get 128. And divide by 2 again. Every time you pick the middle and you choose 1/2 of the list, you shrink the list by by half, right? So 64, 32, and 16, and 8, 4, 2, 2, and 1. Okay, so basically you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times, which is 2 to the power of 10, right? Time, the number is 2 to the power of 10, but you need the 10 times or log of that, log of 1024, which is basically log base 2, then it's like 10 times. You only need maximally 10 times to find any numbers within this list of size of 1024 if this list is sorted. Okay, so that's the basic idea behind a binary search. So now we know the basic principles. How can we code it up, right? Okay, so we're going to use 2 pointers. One is the left pointer, which initially points to the 0 index, which is starting of the list. Okay, and then the right pointer pointing to the end of list. And the list in C++, there's a size function that gives you the size of the vector, and -1 is basically to give you the because we are 0-based index, so that's the last element in the list. Okay, the last element in the list. Okay, so we're basically searching from the left to the right. Okay, and in the closed brackets, that means both boundaries are included. All right, so I'm gonna have to search in the while loop, and I will leave that a question mark because we want to talk about what's the condition that you're done, right? You're done with the searching. So basically, our algorithm is, remember, pick the one in the middle because they're sorted. So I'm gonna pick the middle index. Basically, is left. You want to say the right plus right divided by 2, right? Okay, so there's a small detail that you need to think about is so it's the integer, the 32-bit integer 2 to the power of 32. That's the maximum size it can represent. Now, if you have 2 integers add together, it may exceed the maximum number allowed for an integer. So you will get something like overflow, right? Integer overflow, because at the end you will divide by 2. So maybe the half of the index is within the boundary of the max, making size of integer. But if you add them together, temporarily it will exceed. So to avoid that overflow, it's better to write it this way, which had the same effect, but will avoid this problem, right? So you get a delta, the distance divided by 2, and you use the left to add to that distance. That gets you the same effect, but avoid the integer overflow. Okay, so that's why we need this small trick. Now, here comes the condition that you're gonna tell, right? So you pick the mid, and if let's look at the number in that mid index. If the number happens to be your target, well, you're lucky, you find the answer. So you just return that mid index and you're done, right? Else, if this number in the middle is less than the target, okay? If it's less than the target, then what we do? Think about it, right? And then the other condition is if the number of the midpoint is greater than the target, what are you gonna do, right? And finally, when you are out of the while loop, right, and what are you gonna return, right? So that's a question we need to answer when it comes to the binary search. So first of all, like I said, in this example, if we know that the mid number 3 is less than target, say 9, then we know we don't need to search the left half, right? So the left boundary will be the mid. The mid is less than, so I add 1. So I'm searching the one next to 3, right? Right side of 3. So it's 5. We're starting with 5. We don't need to start with 3 because we know 3 is less than 9. So we're starting with mid plus 1. Okay. And for the right side, it's still at pointing at 9. We don't need to fix the right boundary. Okay, so if it's the other way around, if the number is less than 3, then I only need to search on the left and we can discard everything on the right. So if essentially we're going to say right boundary going to move to mid what? -1, right? Again, we don't need to consider mid because it's not equal, it's greater than the target. So that must not be it. We have to consider everything to the left. So that's the two conditions you can think about, right? And then, because every time you didn't find the target, you're gonna either move the left or the right. So what's the end game, right? So initially the left is 0, right is the maximum size. So left must be what? Must be less than or equal to right, right? If there's only one element, then left is equal to right, okay? Even though if it's one element, you can still get the middle, which is that element again. And if you find it, return. If you didn't, then you'll be out of the loop. And then what? Because if you find it, you always return the middle. So if you're outside the loop and you didn't find it, you can return -1, which is required by this problem. Okay, so far you have finished writing this binary search algorithm. So there's a couple of details you need to pay attention to, such as if you want the right point to the last element or the one above that. So in other words, you want to include the right or you don't want to include right. Depends on what you're gonna do. You will do different in the while the conditions, right? So let's test this out. There's some errors, I guess. Oh yeah, because I only wait a second. Did I nums? Oh yes, I get. There's some nums, and nums. Okay, is that right? Nums. Nums. Oh yeah, this is nums, not nums too. Define here. I'm gonna delete this thing. All right, so run it again. Yeah, the answer is -1. Okay, because I'm looking for 42. If I'm looking for the number 5 and run again, you can get a correct index, hopefully. It's 3. So 0, 1, 2, 3 is number 5. Okay, so yeah, we solved that problem. Okay, so that's the basic idea. Now, let me give you another example, okay, of int nums2. I will give you 1, 2, 2, 2, and 3. All right. So in this example, I want to find not only one target. Like say the target is 2, right? Because you can see there's a multiple 2s here. So not only I want to find the 2. You can use binary search to find the 2, no problem. I also want to find the left boundary of the 2, right? So what I want to give me the index where the first target appears, not in the middle. In other words, I want to find the boundary where the target first occurs. Okay, do you understand what the problem is? So I'm gonna give you some function signature. It's called left boundary. And it takes the vector of nums and the target. So given the target, give me the index of the target where it first appears, right? So in this case, the answer should be 1, right? 0, 1. If you cannot find that target, then return a -1. Okay. So how you approach that problem? Well, some of you may say, okay, we can use this binary search to find the 2. And then after that, we're going to look on the left side and see if there's a number of same value occurs on my left. If it is, then we just continue, to search until we find. Basically, you are doing the linear search after that. Well, if you do a linear search after you find the middle one, or the first one, right? The first one, it takes O of log n, but the linear search takes O of n. Although you only need to search, if you're lucky, you find the one in the middle, you only search half of the n, but it's still O of log n. The worst case scenario is basically it's all the same numbers, right? And then you just need to search, the linear case. All right, so it's still not. So we still want the O of log n. So how are we gonna do that? Well, it turns out it's very similar to how we approach the binary search, right? So we can still using binary search to find the target, right? When we search it, these two conditions, right? If the number is less than the target, we still need to, let's see, if the number is less than the target, then that means we can throw away all the left half, right? So we still do this, and if its number is greater than the target, we throw away the upper half. And if the number is equal to target, that's the difference, right? If we equal to target, right, we search for 2. We don't stop there, right? We continue to look on the left side, and so we keep the boundary, the right boundary in the middle, and we look at the left side to see if we can still find the 2. We still do a binary search after we find the same number, right? We don't stop until we don't find that number. Then the last time we find a number is the one that is the leftmost. Okay, so that's the idea. So let's code it up. The base case is if I'm given a list or array that is 0 size, right? Then of course -1, nothing to search. Now let's still define these 2 pointers. Left is 0 and right is equal to the size. Now this time I do want to well, let's be consistent, -1. So yeah, and then same while loop. Let's it's the same thing, right? Left equal to right. So we don't want to miss the right side. Okay. And then we will still look at the middle point. Left plus right minus left divided by 2. Okay. And then now we're gonna look at these 3 conditions with nums mid is less than the target. Okay, it's the same as the binary search. Left is equal to mid plus 1, right? Because we are searching from mid plus 1 to the right. Okay. Initially, we are searching from left to the right. Okay, all included. And else, if nums of mid is greater than target, if it's greater than target, then right is equal to mid minus 1, right? So basically we are searching from left to mid minus 1, right? Because the mid is greater than target, the target has to be in the left half. So that's the same. Else, if the nums of mid is equal to the target. So we find the first occurrence of number, but we cannot just stop there because there may be more, right? So now what? Because we are looking at the left boundaries, that means we still treat it like we throw it half of the right. So it's basically like the same as the above case mid minus 1. Okay, so that's the only thing that you need to worry about. And also when you're out of the loop, we have to check if the index of the left is out of bound. So what is the condition this will happen is when the target is not found in the list, right? If I give you a target 42 in this list and there's no way you can get a 42, so you keep moving left to the right until left equal to the right, and you're out. But then when you are out, left is greater than the right. So, and that's illegal because the right is basically the last element in the list, right? So you have to check if left is greater or equal to the num size. Because it's zero based, it can never be equal to the size, or nums left is not equal to the target, right? At the end of the day, if you cannot find the target, so you're gonna return -1. Now, if you can't find a target and the left is within the index boundaries, then you can basically return that left. Right? Left points to the leftmost number that is equal to the target. Because every time you find the target, you just keep searching, and if the mid number is less than the target, left is keep adding. If until the left is greater than, remember, equal to right. Our last right is, for example, if your last search, say you stop at where is that example? 1, 2, 2, 2, 3, right? So you say you are on right. The right is the mid. The last mid is index 1, and you are searching to 1 minus 1, 0, and the left is less than the target. Then left is mid plus 1. The mid plus 1, it returns to 2, and it is equal to the right. So it will end with left equal to 2, and that's the answer that you're gonna return. Okay, so that's all for doing that. Let's do a example. So let's copy and paste. Okay. Left bound. So we're gonna do left bound, right? So nums 2, I'm searching 2, and it's going to give me the answer is should be 1, right? Now, of course, you can also use left bound to do the binary search. It will give you the same answer because there's nothing repeated, and what you got is just one number. So if I do that, it'll give me the same answer. it won't change anything. All right, so here you go, the example of left bound and binary search. So the homework for you is, can you do the same thing for the right bound for that case, which will give you 0, 1, 2, 3, right? The answer is 3. How you code this up and change something in this function to give you the right bound. Think about it. Okay, so thanks for watching. Hope you get a better understanding of binary search and its runtime complexity. See you next time. Bye.